Okay, welcome everybody, both people here and to the 200 people that are connected for the webinar. So the webinar is, and the seminar is an RFF-CMCC webinar and seminar. So let me just say one word on that. RFF-CMCC is a joint effort of the Euro-Mediterranean Center on Climate Change and Resources for the Future. Jointly, they funded the European Institute on Economics and the Environment. The mission of the center is on the slide, and I won't use the time of the speaker to present it, but you can read it there. So today's speaker is Roger Cooke. We want to thank him for being here. He's going to take my seat in a second. Roger Cooke is a senior fellow at Resources for the Future. He has been professor both in the US and is still a professor at Delft University in the Netherlands. Roger Cooke is also one of the main person doing what's called uncertainty quantification. He has done a lot of work on various topics. One maybe most very relevant for people attending the seminar and the webinar is his work on sea level rise and the impact of ice melting on sea level rise and the uncertainty quantification of that metric. So today, however, is going to talk about using the social cost of carbon to value Earth observing system. And I just have to say something related to the Q&A session. I'm going to sit nearby, and I'm going to collect all the questions from the webinar. And I'm going to then give you a voice at the end of the seminar, both to people that are asking questions here and people that are asking questions at home. And I hope this will work out. I'm sure it will. So without further ado, Roger, I give you the floor and the computer.
Okay. Thank you, Valentina, and thank you, EIEE, for hosting me for a week. It's been really wonderful, and I really enjoyed the chance to speak with the researchers here. So I understand I'm addressing the virtual people in this way, but sometimes I also look to the real people over here. So I hope that won't be too confusing. I'm talking now about work in which I've been involved for the last 5 or 6 years, calculating the value of information from Earth observing systems. And in this talk, I'm going to show you how NASA has been digesting this work. So, for example, this first slide is a screenshot from a talk that NASA has been, or people from NASA have been giving a lot. And this work has received a lot of play there for reasons which hopefully will be obvious as I proceed. And you see it's done by 4 people at NASA Langley, and myself and Sasha Golub at American University. And it starts off with the system called CLARREO. And when I met these people for the first time, their funding had just been yanked, as we say. Congress had stopped the funding of this project, and they were very unhappy about that. And so the moment I came to talk with them, I was able to give them a ray of hope in a way. So let's just jump right in. These first sheets are taken from the NASA talks. So they typically begin with some bullets like this. Science is an economic investment by the public, of course. We have no climate observing system. Now, the world has no climate observing system. Everything that we learn via satellites from space involves piggybacking on other systems that were designed for other purposes. So, should we have one? Is it worth it? What is the economic value of an advanced climate observing system? So this is the main challenge which I took up from them and tried to do something about. And it concerns in particular this system, Climate Absolute Radiance and Refractivity Observatory, CLARREO, which is described in a publication of 2013. And Bruce Willicke, who's a co-author on all of these, is also the lead scientist for this project. So CLARREO is seen as a first step towards building a climate observing system. So I'm going to say a little bit about CLARREO. The problem is that to observe climate, you have to have long, accurate time series. And most of what we now know from space-based systems about the Earth is piggybacked from weather satellites. And the weather prediction problem, there's a lot of money in predicting weather, as you can imagine. But the weather problem is a 2-week initial value problem. So you really can't use more than 2 weeks of data in order to predict the future for the weather as far as you can. So a typical weather satellite has a design life of about 8 years. And in the course of this 8 years, it will slowly be degrading, and its orbit will be degrading, and its instruments will be degrading. And when it sort of falls out of the sky, then they shoot up another. That's basically how it works. Now, you can understand that with this system, you will never develop the long time series of very accurate measurements that we need. And that's what CLARREO is designed to do. So the original design involved 2 measurement platforms, one measuring the global surface temperature of the Earth, and the other measuring cloud radiative forcing, which more or less comes down to measuring the radiation imbalance at the top of the atmosphere. And so just to give you an idea, realize that a decadal rate of temperature rise of 0.2 degrees centigrade, that would lead to a warming of about 2 degrees centigrade over 100 years. That's what we're talking about. 0.2 degrees centigrade per decade. That's what the accuracy that's required. That's what we need to be able to do. And so CLARREO is designed to do that. And in the Congress, if you have a system that contains the C word for climate, Congress will defund it. That's the world in which we live. So that was the situation at the moment that I got in touch with these people. And now this again is another slide from the NASA talks. And they are using 3 basic tools to compute the value of information of climate systems. And here you see, first of all, if you can see my mouse moving here, the integrated assessment models, in particular DICE, are being used extensively. And then the interagency memo on the social cost of carbon being used extensively. And then from the designers of the CLARREO system, from the designers of the CLARREO system, the uncertainty decomposition that they had performed in order to motivate their system as an improvement over existing systems. So it's these 3 components that go into this. So notice that these integrated assessment models are really being used. And the thing that makes it possible for us to use them is this social cost of carbon memo. And that's one message I would like to impart to you. Though these things have had a real impact, at least on people like me. Okay, so now let's talk a wee bit of mathematics, and let's talk about the uncertainty in observing a trend. So here we have a trend, x per unit time, and we're measuring x at equally spaced time intervals. And suppose we have measured these 5 points, and we want to know the trend. Well, we will make some regression there, and we will estimate the trend. Now we observe one more point up here, and this trend line moves. So this movement of the trend line reflects the uncertainty in the trend, which we have after an initial series observation. So the governing equation for this is as follows. The variance in the rate of change of x is equal to 12 divided by the 3rd power of this total interval of observation times this thing. And this thing is the variance contributed by natural variability times a characteristic time for natural variability plus the variance contributed by the calibration. calibration noise times its characteristic time, plus the variance contributed by orbital decay times its characteristic time. This is assuming that these sources of error are all independent, of course. And these characteristic times are basically the sum of the squared autocorrelations between successive observing intervals. This equation is derived in time series analysis in linear models. It's nothing spectacular, but just to, well, it is of course spectacular, but it's well known. And this is the main mechanism for us to be able to control the uncertainty or observation of climate trends. So what the NASA folks did was to quantify these sources of uncertainty. So you see here, we're looking at decadal temperature rise, and we're showing here the standard deviations, and I'm showing them for the improved CLARREO system, this COS is climate observing system, and the current system, which is anachronized as IAC. And so you see the natural variability. This is the one period variance that's caused by natural variability. Is 0.085 for both systems, and the characteristic time is 2.3 years. The calibration uncertainty for the existing system is 0.18, and for the new system is 0.03. So here is the big reduction in uncertainty. And the orbital sampling is about the same. So this is the analysis that the folks at NASA have done in order to motivate their system. And there's a similar plot with respect to cloud radiated forcing, about which I will say relatively little in this talk, just in the interest of time. And then the people at NASA produced this graph, which is rather complex. And I'm just going to try to explain it very briefly. The horizontal axis here is called, this is their words, the trend uncertainty, degrees Kelvin per decade, 95% confidence. And these colors represent different observing systems. So the way to read this is as follows. If you want to be 95% certain that the decadal rate of temperature rise is at least 0.2 degrees centigrade, then you have to observe this system for a little over 10 years if you have a perfect observing system. A perfect observing system is subject only to natural variability. We can't get rid of that, right? But perfect in the sense that there's no calibration error and no orbital decay. Then if you go a little farther, you hit the CLARREO line. So you see CLARREO will give you this 95% certainty in about 13 years. And these last three lines out here, these are the current systems according to how you use them or which ones you believe. You're out here in the neighborhood of, say, 25 years. So this picture doesn't show you how likely it is that you're going to observe this. Let's say if you want to observe this with 95% confidence, you're going to wait 13 years with CLARREO, and you're going to wait, say, 25 years with the existing. So when they presented this to me, I said, fellas, this is worth a lot of money. This is worth trillions. And they said, did you say trillions? Yes, trillions. Anybody who's worked with these integrated assessment models knows that you get these kind of numbers. So that was the beginning of a beautiful relationship. And in order to convert this reduction in uncertainty into dollars, we're going to use the integrated assessment model DICE in connection with the social cost of carbon memo. So first of all, we have to talk about the probability of observing these various rates. So we have here these two pictures. This is cloud radiated forcing over here. This is global temperature. I'm going to focus on this one over here. And now if I use the environmental model that's in DICE, then you can make this type of picture. As a function of equilibrium climate sensitivity, I can plot the decadal rate of temperature rise. You can pull this out of the model, right? So for example, if equilibrium climate sensitivity is 10, by the way, do you have a sheet of paper that I could put this mouse on? Somebody have a sheet of paper? Just, the mouse is rather unresponsive. Excuse me. This is harder than it sounds. Okay. All right. Here. Okay, that should help. Right. So here, equilibrium climate sensitivity is 10. That means that the decadal rate of temperature rise starts at around 3.5, and then in the course of 100 years moves up to about 5.5, say. If, on the other hand, climate sensitivity is 2, then we're down here, and we start at about 1.5, we move up and then gradually fall back. So what this means is, according to the model that underlies the social cost of carbon, and that's what we're using, according to this model, if I could observe this decadal rate of temperature rise without any error, I could uniquely infer the value of equilibrium climate sensitivity. Now, the physics people in the room will object, of course, and of course it's not that simple, but this is the beauty of the social cost of carbon memo, because it relieves us of this proof burden. We don't have to argue that this is true. We simply say this is our policy. This calculational platform has been approved as the way to value releases of carbon into the atmosphere. So we're just following policy. That was a very important step. Now, what happens when we start observing? We observe these values on the vertical axis with noise. So, for example, in 2035, I may have this uncertainty about the decadal rate of temperature change. If I go out to 2075, I'm up here. And notice here with cloud radiated forcing, I just want to point out, these lines are further apart, but the system that's measuring them is also noisier. So it's complicated. You have to really get into the numbers and work it out. So this is the picture for the enhanced systems based on the uncertainty decomposition of the NASA people. And this is for the existing systems. This is just a cartoon, of course. These are not real numbers. It's just to give you the idea that for the existing system, these distributions are much wider and they shrink more slowly. Okay, so here's the program. And the fundamental insight underlying this work is that information can only have value if it's used, right? And this was also in your paper, Massimo. I noticed this is a very natural thought to have, and Massimo did a nice paper in which he valued information in this sort of a way. So you have to posit a decision context in which the information is used. Now, I've had many discussions with people, economists in particular, who say, well, yeah, but how can you prove that they're going to use it? That's not my problem, right? Look, I have 100 Swiss francs in my wallet that I've been carrying around for a long time. And if I never get around to cashing it, I will never use it. And I will never have any value extracted from that. But it still has value, right? It has value, which I am not harvesting. So the problem is not to prove that someone is going to harvest this value. The problem is to quantify the value that's out there and available to be harvested. This is, I think, a really important idea that makes this problem a little bit tractable. So we have to stipulate a decision context. So the decision context for this work is as follows. When we become 95% certain that global surface temperature rise is at least 0.2 degrees per decade, then we will switch to a reduced emissions path from business as usual. Up till then, we're on business as usual. And if we get this signal with 95% certainty, then we switch to reduced emissions. And the reduced emissions can be either the DICE optimal emissions path or the 2.5 stabilization path or the Stern-Gore path or anything else. But we're going to look just at these three, okay? So how does it work? First, we choose a decision context. Then we sample a value for equilibrium climate sensitivity from the truncated Rowe-Baker distribution, which is mandated by the social cost of carbon memo. Just following orders, right? Just doing what they say. So, and then we compute the year in which that trigger value will be exceeded, both for the existing system and for the new system. That's the computation that we can do thanks to the uncertainty decomposition of the NASA Langley folks. So when we have done that, then we can compute from the time at which we pull the trigger, we compute how much damages we avoided by not staying on the business as usual path after that time. And we compute that for the new system and for the existing system. The existing system will typically pull the trigger much later, so they will stay longer on the business as usual path. They will incur more climate damages, and we take all that and we discount it back to the present, and we compute its net present value, and that is the expected net present value of the excess averted damages if we adopt this new system. Okay, it's a mouthful, but you have to, the idea isn't so difficult, but it's a whole bunch of words. So that's what we're computing. And we do that in the first instance for the damages, because the social cost of carbon method concerns only damages. So we wanted to stay as close as possible to the social cost of carbon platform. Later, we also did it for net benefits. And in doing this, we hardwired the reduced emissions path. So we stipulated at the beginning, we're going to adopt the DICE optimal or the 2.5 stabilization or whatever, and we use that throughout the whole period. Then we go back and we draw another value from the Roe-Baker and we build up. So that's the basic idea of how it works. Then having done that, we will vary these parameters of the decision context in order to make sure that our result is very stable. Okay, so here's a picture that gives another picture of that same thing. What we're showing here, I hope you can read it, I guess you sort of can. This is the perfect observing system. Yellow is the CLARREO system, the enhanced system, and purple, I guess it is the current system. And on the horizontal axis, we have the value of equilibrium climate sensitivity. And on the vertical axis, we have the year in which the trigger would be pulled, where we switch to the reduced emissions path. And this is the base case where we launched in 2020. We're requiring 95% confidence, and we pull the trigger at 0.2 degrees centigrade per decade. And so what you see here is that it depends on what the value of climate sensitivity is. So if climate sensitivity is 3, then you see that the enhanced system will pull the trigger in 2045. The current system won't pull the trigger, where did my mouse go here, until 2060. That's 15 years. 15 years we're going to be racking up these climate damages, which would not have been necessary had we had the enhanced system. If we get out here to very high values, say climate sensitivity is 6, then this is a very strong signal, and the existing system will pick it up, right? And so the difference between what happens with the existing system and what happens with the enhanced systems goes down. So the big bang for your buck is actually here in the middle. For these types of climate sensitivity values, this is where the enhanced system is going to most outperform the current system. Then you can change all these parameters. For example, here, I move the trigger up to 0.3 degrees centigrade, and that has the effect of just pushing this picture to the upper right. And you do all of these variations in your decision context. That's all ingredients in the calculation. And so now we can give some picture of the results. So what we're showing now is net benefits. And I'm showing the excess in net present value expected, I guess it should be expected net present value of the net benefits that we get by triggering on the enhanced system versus the current system. And we do that for 3 different reduced emissions paths. This is the DICE optimal, this is 2.5 stabilization, and this is the Stern-Gore path. And so what you see is that for low values of climate sensitivity, the 2.5 stabilization path will be giving the highest excess expected net benefits. relative to the existing system. As climate sensitivity increases, you see at some point, somewhere around 4, that the best option is the Stern-Gore path. Best in the sense of best improvement above the existing system. And if the discount rate is bumped up to 3, you see this picture. Note that the scale here on the vertical axis is always the same, from -5 up to 35 trillion US dollars in 2008 dollars. And so you see everything goes down, of course, and you see that the 2.5 stabilization stays competitive longer. Eventually, the Stern-Gore reduced emission path is going to win for very high values of climate sensitivity. Now, this is interesting. You have to put your glasses on here because I'm using the same scale. So if I look at this with 5% discount, which is what DICE uses, then you see indeed right here up to 3, up to 4 maybe, that DICE is the optimal, right? And that's not so crazy because it is optimized for that climate sensitivity. And with this discount rate. And you see that Stern-Gore is actually going under 0 for quite a while. So Stern-Gore is losing money. So this says, relative to the existing system. So this says, with this discount rate, Stern-Gore is not a good idea. And implementing a not good idea is better to wait longer to do the bad idea than to do it earlier. That's kind of this always requires a little bit of explanation, but once you see what's going on, it's all makes perfect sense. So now I'm going to show you some of the results of our sensitivity analysis. And this here, the top line is the base case, and I'm showing you here just the averted damages. So you see that for this base case, 95% confidence, 0.2 degrees centigrade per decade, that the surfeit expected net present value of the averted damages at 2.5% when I go to DICE is 17.55 trillion. At 3% discount, it's 11.67 trillion, and at 5% discount, it's 3.14 trillion, and so on. And now I change these parameters, and this is just giving you a few examples of the stuff that you do to demonstrate the stability here. If I move the confidence level up to 97.5, what does that mean? It means actually that the current system is going to have a harder time pulling the trigger than the enhanced system. So the difference between these two systems is going to stay larger and longer. And that means that the benefit of the enhanced system goes up. If we go to 0.3 degrees per decade, you see something similar. And again, the reason is that the existing system just has to work harder to get that trigger pulled. And that means that we spend longer in the business as usual regime under the current system than under the enhanced system. So this is the kind of analysis, but if you let your eyeball just wander over here, whatever you do, you're talking tens of trillions, unless you use 5% discount, and then you're talking a couple of trillion, right? So that's the basic message. You posit a decision context in which it's used, then you vary the parameters of that context, and the whole thing makes perfect sense. And so this sheet collects some of the results that I'd like to show you, the difference between looking at averted damages versus net benefits, and the difference of using a real option approach, which I will explain in a second. So here we're looking at averted damages. If I use DICE optimal at 2.5 discounting, the surfeit, the excess expected net present value of averted damages is 17.55 trillion, right? If I look at net benefits, it's 9.99 trillion. So net benefits, I'm accounting for the cost of the mitigation that's involved in switching to the DICE optimal path. So that costs just about almost half of this amount, right? Is what it costs. And for 3%, you see you go down from 11.67 to 5.93. And at 5%, you go down from 3.14 trillion to 0.99, okay? And that picture is basically the same for the others. Note here that for Stern-Gore, at 5% discounting, the net benefits are negative, right? We're spending more on mitigation than we are winning by switching early, right? Now, this analysis assumes that we choose once and for all at the beginning which of these things we're going to switch to, right? You could also say we will choose after we observe, because if we observe very early that the trigger is pulled, that tends to mean that climate sensitivity is pretty high because the signal is so strong that we're observing it early, right? So if that happens, maybe we want to go to Stern-Gore, right? If you think of that previous picture, because then you're out towards the left where the green line is dominating. On the other hand, if you pull the trigger late, that probably means you're in a moderate value or low value for climate sensitivity, so you're better off choosing one of the others. And so the question is, how big is the added value of adding this real option feature to the model? Well, you see here, if I look at the surface net benefits, these are net benefits. For 2.5 discounting, the best I could have done would be the 2.5 stabilization scenario. If I include this real option feature, then I can earn 16.7. That's only $1 trillion, right? No big deal. But there is a difference, and there is an advantage of exercising this real option. So here, if you're using 3% discounting, the best would be, again, 2.5 stabilization. But for those cases in which the climate sensitivity is very high, I could switch to Stern-Gore and win a little more. And so you see that's the way this all works. So the bottom line is that the additional cost of these climate observing systems is on the order of 10 billion per year. Over a 30-year lifetime, that comes to a lifetime cost of, say, 200 to 250 billion. That's a fairly small fraction of the value of this information. And that's the message that the NASA people very much like to hear, and that they've been promoting this. So, and for an economist, I think this is not strange. These numbers are big. The world economy is big, you know. There's a lot of chips on this table, right? So there's a lot to be done. And I would say there's a lot more work in this area that we can sort of get involved in. The last sheet is going to show you the difference between global surface temperature and cloud radiative forcing. And the reason we did this is the following, that the original system was designed to do both. Then they were told, you can't do that. You have to cut your system down so that it can be done from the International Space Station. That's just an add-on, right? It's not going to have you're not going to have your own satellites for this. You're just going to piggyback off the space station. Which one do you want? You can have one. And this analysis shows that the value of the information of measuring cloud radiative forcing is much higher than measuring global surface temperature. That sounds great, but the real reason for that is that the current system for measuring this is much worse. That's why it's so much better. Now, this analysis was conducted after the fact because they had to choose in 2016 which one they were going to do, but after the fact, we could analyze it and show in this sense they made the right choice. So that's basically the end of the talk. I want to point out a couple of publications here. This one by a whole bunch of people. You see this, with the exception of myself, this is pretty much all the heavy hitters in the US in the climate world, right? I'm a free writer on this one, but and this article is a plea for designing and implementing a global climate observing system, which we don't have. And this has to be an international effort. It has to be Europe, Japan, China, USA. But the sobering fact is that we don't have this. And there's a lot of money on the table here. So there's plenty, if we get the economics right, it shouldn't be hard to motivate this idea. And then the other things are papers that have been produced by the group that I mentioned. Okay, so what is the future? We at RFF are currently updating the computing platform for the social cost of carbon. So the DICE model is probably pretty much exhausted its shelf life, and other things will be coming down the pike. An interesting question is how we combine disparate lines of evidence. So this, I didn't talk much about it here, but here we had the issue of deciding whether we're going to measure global surface temperature. This looks like should be an S, global surface temperature, or cloud radiative forcing. How do you make those kinds of trade-offs? How do you make those decisions? There's an interesting line of work there. And then developing the economic case for a climate observing system. And a new thing that I'm getting involved in is carbon cycle uncertainty, and can we do something similar for valuing reductions in uncertainty in the carbon cycle? Okay, that's it. Thanks for participating, and I'm very happy to take questions.
Okay, the way we work forward now is that we're gonna read out questions, or I'm gonna repeat questions if done by people here. I have a question that was made at the very beginning by Bernd Ecken, who asked what about Copernicus, especially C3S, and I'm talking about something that together with Sentinel satellites provides a huge Earth climate system observatory. So the first question is about the existing system.
So I'm sorry, I don't know anything about that. Is that a European system, an ESA system? So maybe somebody can say something about it, but I can't.
So while you ask questions,
that was a fairly disappointing response.
I think.
Okay, any other question from here? Okay, you asked a question and then
Johannes had a question.
Johannes asked and then I repeat, or if you want
to. Just maybe two questions about the framing and the decision framing.
Yeah.
I mean, of course, you start from the point of view that kind of the baseline and then there's policy, but you could also start with the question. It's maybe that devil's advocate, but you could also look at the problem like imagine we do a kind of policy, let's say the Paris Agreement kind of gets implemented, yes. And then we see at the lower bound that we are maybe there. So what is the risk there? I mean, I think that could be also interesting to see what happens in this case. And also the second question is about the 95 percentile, because you could also look at the lower range. So I mean, also there's a kind of risk in a value of information. So I don't know. It might get different values, or just to opinion on that.
So you could lower this confidence threshold so that you pull the trigger at 90% confidence, or you could look at, you want to be sufficiently certain that it's less than 0.2 degrees. You could do it different ways, yeah. That makes sense. We didn't do that, but it makes sense to try it. Oh, this, yeah, so.
Can you repeat the question?
So the question was, what about evaluating an optimal policy in this way, or did I understand? Maybe you can repeat that.
Two stringent climate policy, which like the current Congress might use, and what is the risk of that? And then you learn that it's actually lower, and you have too much, let's say, abatement.
Yes. Yes, that's of course possible. That's of course possible. So if climate sensitivity is very low, oh hum, right? Not much motivation to switch to something like a Stern-Gore thing. But the emphasis here was to value the additional information, not to choose an optimal policy.
When you compare your results with the cost of what we're doing, so okay, it's still I think you will never do this.
Yeah. Yeah.
And because of that, we still why is the cost related to the cost of having invested on the
I'll repeat the question. The question was made, what would be the potential benefit of having a better system in the case, though, that we are overdoing mitigation policies? So is there a value to have a better system also in the other direction if we are doing, which is sort of unrealistic today because we are not overdoing climate mitigation, but let's assume we start to go down the 1.5 degrees Celsius path tomorrow. Is there still a value of improving the system if we do that and then we discover that we actually should have done less? So, can we extract value in this other direction as well?
The cost of investment because having overdone or having.
Right. So, but if we want to value the information, so we've got to convince somebody to spend 10, 20 billion on the SEME. So if we have decided a priori we're going to go down the Stern-Gore path, then we are running risks. We are running risks of burning a lot of money that wasn't necessary. So we want to reduce that risk by first observing and then choosing. That's the whole value of information framework, is first observe, then choose. And that's always better if the observation is free, which it never is, but that's always better than just choosing and then observing.
Yeah, I mean, the damages in DICE, the damages in DICE are very small in the standard DICE model compared to some of the other estimates. So actually, if we were to do the analysis, keeping as a fixed point 2 degrees or 1.5 degrees as an endpoint, I think the value of information would be even much larger than this by default, because essentially you have to hit our target, which is automatically more stringent than what would be implied in an optimal DICE, which goes to 3 degrees, not even to 2.5. But of course, this is all the normative analysis, assuming the whole world is, decides to comparatively reduce emissions once you get the trigger point of 0.2. Whereas we know, in fact, that even if that happens, and it has already somehow happened, we're already at +1 degree, of course not per decade, but cumulated, and yet we have not reached a comparison. So I was wondering whether the value of information could have any value also, or more the regional incentives or the strategic incentives towards cooperation on climate change. After all, I mean, we also try just quantifying the loss and damages, which is also a huge discussion right now. And developing countries are already bringing this up a lot. And already each decade, by being a bit more sure that you're observing temperature, which is actually effectively associated with greenhouse gases and not natural variability or any other effect, I think the claims over loss and damages would certainly be higher. That by itself be useful for triggering more action on CO2 emissions. So I don't know.
Yeah, yes to all of that. Okay.
I have to repeat for the people at home. That's what I've been asked. So, and I don't know, but you should have come closer. That's the point. So, the main point made was that if you were to evaluate an emission pathway that is in line with 1.5 and strictly to that, the value would be larger, and if the reasoning would also be applied to the evaluation, a better evaluation of loss and damages. I'd like to.
So yes, thank you. I obviously agree with everything you said, and I think you point to an interesting thing. Can this be regionalized so that we can go to various regions and partners and say, look, not only is it in the interest of the world, but it's in your interest to do this. And I think that's an option, but that's outside the original social cost of carbon framework. So that wasn't an option, but of course, with systems like which, you could easily do that.
Also, the paper of me will come to that social cost.
Ah, okay. All right. Yeah, that's very useful.
Now I'm reading a question from Jeremy Norget, and sorry for any mispronouncing your name. So, do you value more the precaution option, meaning waiting for more information, whereas action should be taken now? If yes, is it only because in this way we give an insurance to the finance banking system to invest in mitigation?
Do I prefer the precautionary principle?
Do you value more precaution option, meaning waiting for more information, whereas action should be taken now? If yes, is it only because in this way we give an insurance to the finance banking system to invest in mitigation?
Well, for me personally, I would advocate aggressive mitigation now. And you can also design more and less intelligent systems for doing this, but I would say that this is my personal view. It's not a result from this study, but that it makes a lot of sense to mitigate now. And if it appears from our enhanced observing systems that we are over mitigating, it's pretty easy to pull back and adopt. But that is not the result of some optimization on my part. It's just my personal opinion. Yes.
Okay. So I just had a comment about the value of information. So you used climate sensitivity as the source of uncertainty, but just to keep the framework of DICE, we know, as Maximo was mentioning, like damages are very uncertain. So I was thinking maybe, by conducting a much cheaper survey and analyzing things on the earth, what we have on the field, we can gain more valuable information and calibrate the damage function in the DICE and compare that value of information that you gain from that survey in a much cheaper way. So when you are talking about building this satellite and sending it on the orbit, so I think you have to compare it with other options that you have to reduce uncertainty in different sectors of the DICE model.
Yes. Yes, thank you. That's a good remark. And this analysis just focuses on two of the possible measurement platforms that you would get if you launch this whole system. But of course, there are other things. And in evaluating the existing systems, this group was only looking at existing satellite systems. And there are other things which are coming online now, like the Argo system for measuring sea surface temperature and this sort of thing, that will be very relevant. And it's an issue that I've bumped up against in doing this work, is how do we compare these different measurement platforms? How do we decide which is giving us the most value for the information? So this is just really the first effort in this direction, that we just tried to figure out how to get our heads around this question at all. And the next step will be doing things like what you suggested, and certainly in the new social cost of carbon platform, there will be much more to say about the damage function.
So before we close, I think we should give an answer to the first question. I tried to better answer as much as I could. I don't think C3S or Copernicus have their own satellite. Or they are data storage. They collect data of various sources, but they don't they don't have a satellite out there collecting data for long-term temperature predictions. That's what I'm seeing on their website. But if I'm wrong, and if you're out there and you know I'm wrong, please, you can send a comment right now on the webinar. Okay, then I think we can close here and we can give a round of applause and thank you for all at home.